The science behind manifestation. Many people, especially those with materialistic worldviews, are under the impression that the law of attraction is nothing more than pseudoscience. And whilst it is true that many people within this community use either incorrect or unproven scientific claims to try and back up manifestation, it's not true that manifestation has no relation to science. In this video, I'm going to explain how the law of attraction correlates to quantum physics, because there are some interpretations within quantum physics which offer support for this idea that our consciousness can influence our physical reality. My name's Georgia. I'm currently studying a master's degree in consciousness, spirituality and transpersonal psychology, and one of the things that I absolutely love to do in my free time is explore the links between science and spirituality. So I've done a lot of research into how science correlates to manifestation, and one of the areas where it really correlates is of course quantum physics. I'm sure you'll have heard this if you've watched any manifestation videos. But in this video I want to go really in depth into it, and I'm going to explain to you two specific interpretations of quantum physics. One of them offers support for how our consciousness might influence physical reality, and the other interpretation provides a potential theoretical basis for the idea of quantum jumping. And two disclaimers: I am obviously not a physicist myself. I have done my best to research this deeply and as accurately as possible, but I'm obviously not immune to mistakes. A lot of what I'm going to talk about in this video I actually got from this book. Now, this book is amazing for anyone who wants to understand the basics of quantum physics. Well, it's not really basic. Nothing about quantum physics is basic, but this is a really good introduction to it all and a great overview. And then the second thing I want to briefly mention, as I've already alluded to, it is interpretations within quantum physics that link to manifestation. So it's not proven. Basically, even though quantum physics and quantum mechanics has been a hugely successful field, no one ultimately knows what the meaning of it is. So there's this huge debate about its meaning, and there's all of these different interpretations, and no one knows which one is correct. It just so happens that two of the interpretations seem to correlate well with the law of attraction. So before we get into all of the really in-depth quantum physics, there's a little bit of background information that will help us understand the experiments and what's going on later on in the video. And it may not be clear at first how all of this links to manifestation, but I promise if you stick with me, it will eventually come clear. But for now, just keep in mind, anytime I'm talking about a particle being in a superposition of different states, then think of that as the potential realities that you could manifest. And then when I'm talking about a particle in its physical form, being a single discrete particle, think of that as the reality that you want as manifested into physical reality. So the first little bit of background information that's worth knowing is about the nature of waves. And when I'm talking about waves, I'm talking about waves in physics. So light waves, for example, or sound waves. So all of these different types of waves, they have certain properties. Now, one of the key properties of waves is interference. And this means two waves interfering with each other. When they interfere with each other, they create an interference pattern. Now, another property of waves is diffraction. Now, diffraction is what happens when waves go through a very small gap and they then spread out. And then finally, the third property of waves that I want to mention is refraction. So refraction is what happens when waves go through some sort of medium and it causes them to bend. So think of light, for example. If light goes through some sort of transparent medium like glass, then it causes the light to bend. So these properties of waves are worth keeping in mind when we look at the quantum physics experiment. Particularly, remember this idea of interference, of waves interfering with each other, and remember the idea of diffraction. Now, the other bit of background information I just want to briefly touch on is the nature of light. So I've already mentioned that light can act like a wave in the example of refraction. And this was the view of light for a very long time. It was believed that light was a wave. Now, one person who disagreed with this was Newton. He thought that light was made up of particles. However, the prevailing view at the time was that light was a wave, and this was confirmed in an experiment by Thomas Young called the double slit experiment. Now, it's worth explaining this experiment in detail because this is the key experiment when it comes to the quantum physics interpretations as well. So what happens in the double slit experiment is that we have a wall with two slits in, and then we have a back wall as well. So what is done during this experiment is that something is fired through these two slits. In the case of the double slit experiment that was done by Thomas Young, he was firing light through the two slits. And what he found when he beamed light through the two slits is that an interference pattern was created on the back wall. Now, we've already talked about the fact that interference is what happens when two waves interfere with each other. So this experiment essentially proved that light was a wave. The waves of light would go through the two slits, so split into two waves, and then interfere with each other on the other side, causing an interference pattern to emerge on the back screen. So this experiment settled the debate about light, at least it did for a while. That is until about a century after Newton had suggested that light acted like particles, Einstein came along and he actually proved that light could also act like particles. So we know that light acts like a wave from the double slit experiment, but Einstein showed through something called the photoelectric effect that light could also act like particles. So this led to something called wave-particle duality. So now it is understood that light can act as both a wave or a particle depending on what circumstances it's in. So in the circumstances of the double slit experiment, light acts like a wave, but in other circumstances, like the photoelectric effect, light acts like particles, so it can be both, just never at the same time. So this is something to remember as we go on to the rest of the video. It's not as clear-cut as waves are waves and particles are particles. In some instances, certain things can actually be both a wave or a particle. So now with that background understanding, we can dive into the quantum physics. So to understand these quantum physics interpretations, again, we need to look even deeper into the double slit experiment. So this is the key experiment where all of this kind of confusion within quantum physics stems from. So we've already looked at what happens in the double slit experiment when light is sent through the two slits. It acts like a wave. But what would happen if we send particles through the two slits? So before we look at what happens to quantum particles, let's just imagine what would happen if we send sand through the two slits. So let's just rotate the experiment for a second and imagine that the two slits are on the top and that sand is going through the two slits onto the bottom. So what would happen in this case is obviously the sand is going to go through the two slits and create two piles directly under the slits. That is what we'd expect to happen because these are individual particles that are going to build up. They're not waves, they're not interfering with each other, they're just particles and they're going to create two piles at the bottom directly under the two slits. So that makes sense. But what happens when we send quantum particles through the two slits? Now for the purposes of this, I'm going to talk about electrons, which are a type of quantum particle. Now, before we look at what happens when they go through two slits, I just want to briefly touch on what happens when we send electrons through one slit, because this is also interesting and hints at what is going to happen with the two slits. So what happens when we send electrons through just one slit is that we do get one clump on the back wall directly opposite the slit, as would be expected. But that clump is actually slightly spread out a bit. Now this is slightly suspicious when we think back to diffraction, which is a property of waves, where they go through a small opening and it causes them to spread out. However, maybe in this case, this spreading out can be explained away by the particles just bouncing off the edges of the slit. But what happens when we send electrons through two slits? So what we'd expect to happen when they go through two slits is to get the two clumps on the back wall in line with the two slits, as happened with the piles of sand. But what happens when we send electrons through is instead of getting these two clumps, we actually get an interference pattern. Now, as we've already discussed, an interference pattern is what happens when two waves interfere with each other, and yet we're sending particles through. So why are we getting an interference pattern, which is characteristic of waves, even though we're sending particles through the two slits? Again, in this case, maybe we might think that the electrons are simply bouncing off each other and that is somehow creating the interference pattern. But this is actually not the case because the interference pattern still builds up even when you send the electrons through one at a time. So far, when we send quantum particles through one slit, it seems like there might be some diffraction happening, which is characteristic of waves. And when we send the electrons through two slits, we get an interference pattern, which is again characteristic of waves. So it seems like the electrons are behaving like waves. It seems like in the double slit experiment that they're going through both slits at the same time, just like how a wave would do and then interfere with itself to create the interference pattern. So this is already very mysterious, but here's where it gets even more mysterious. So to try and work out what on earth was happening here, scientists use measuring devices or atom detectors to try and figure out what's going on. However, what happens when you place a measuring device behind the two slits is suddenly, instead of getting the interference pattern that we're getting before, we do now get the clump pattern, which is characteristic of particles. So when the measuring device is present, the interference pattern disappears and the particles start acting like particles again. So the question is, what is happening here? What is happening to the particles, or how are they behaving when we're not measuring or observing the experiment? The interference pattern implies that they're behaving like waves, but can we say that they are actually physical waves when we're not looking? Like with light, the wave-particle duality of light. In some instances it's a wave, and in other instances it's a particle. So can we say the same thing for these electrons? Now, this is a very difficult question to answer because as soon as we observe or measure the experiment, we change the result. So we have no way of knowing what's going on when we're not looking or measuring. So we do not know the nature of the particle when it's in this very mysterious state and creating an interference pattern. The best that we can do to understand the particle whilst it's in this mysterious state is use something called the wave function. Now, the wave function is a mathematical quantity, and you get it by solving what's called the Schrödinger equation. And what the wave function does is it gives us the likelihood of finding a particle in a particular place. So it basically gives us probabilities for the location of the particle. And it can also assign probabilities for other properties of the particle as well, but we're just talking about location in this example. So as I mentioned, the wave function is a mathematical quantity, but no one knows what it ultimately is or represents. Some physicists believe that it is just that, it is a mathematical tool and it doesn't represent anything real. Other physicists believe that it does represent something that has an independent reality, so maybe a physical wave, for example. But ultimately, we do not know, so for now we can just think of the wave function as a mathematical tool that allows us to describe the behaviour of the particle when we're not looking at it. However, the interference pattern that's produced in the double slit experiment is very real. So doesn't that imply that there is a physical wave going through the two slits, or that at least somehow the particle is going through two slits at once? Now this is where the idea of superposition comes in. So superposition is a term in quantum physics which means that a quantum particle can be in multiple different states at the same time. So in our example, it would mean that the particle is going through both of the slits at the same time. It's in two positions at once. So the question is, could this really be happening? Now, there is a device called an interferometer, which suggests that superposition really is a property of quantum particles. So what this device does is essentially it's a device in which we send particles through one at a time. And that is a key thing to note, they are going through one at a time. So we send a particle into this device, and essentially the device splits into two different routes. So the particle is faced with an option of going through these two different routes. And then what happens is this device later on recombines these two routes. And what happens is at the end, when these two routes have been recombined, we get a signal that is the result of two waves interfering with each other. And the only way to explain this is that the particle must have gone down both of these different routes at once and interfered with itself at the end. So what the interferometer does is that it shows a particle really can be in a superposition of two states at the same time. Now, as I mentioned at the beginning of this video, remember that superposition is one of the things that links to manifestation. Think of this superposition of states as the multiple different realities that you could imagine, that you could manifest. So a quick summary of what we've gone through so far. So we know that in the double slit experiment, when we're not measuring or observing the experiment, the particles produce an interference pattern which is characteristic of waves. Now, we don't know that they ultimately are waves in this state because as soon as we look, we change the outcome of the experiment. And we also know that when a measuring device is present, the particles start acting like particles again. So for some reason, a measuring device seems to cause the interference pattern to disappear and the particles to act like particles again. Now, this transformation from the interference pattern to the particle being in an actual particle state is called the collapse of the wave function. So again, you might be able to see how this question relates to the law of attraction. So we're going from the particle being in a superposition of different states, which could be said to translate to the multiple different potential realities that you could manifest. We're talking about that superposition transforming into one discrete particle. In law of attraction terms, we're talking about those potential realities manifesting into one physical reality. So the question is, what causes this collapse of the wave function and what does it have to do with measurement? So this is what's known as the measurement problem in quantum physics, the question of why taking a measurement would cause the wave function to collapse. Now, there are many different interpretations of what's going on here, or what's going on in the double slit experiment more generally, and none of them are proven. So essentially we have all these different interpretations within quantum physics which give vastly different implications about the nature of our reality. So now I'm going to go over firstly the main interpretation within quantum physics, and then I'm going to go over the two interpretations which correlate to manifestation. So the main interpretation within quantum physics is the Copenhagen interpretation. Now there are many different versions of it, however there are a couple of key ideas that all of them have in common. Now the main part of the interpretation is that the wave function collapses upon measurement. Now, of course, this is what we've already been discussing, so it really doesn't add anything to what we've looked at so far. In fact, the Copenhagen interpretation doesn't really give us all that much. It could actually be described more as a philosophical stance, and that's because it doesn't tell us how the measurement causes the wave function to collapse, and it doesn't tell us what the nature of the particle is when it's producing this interference pattern. In fact, the Copenhagen interpretation says it's actually completely meaningless to try and ask what is going on when we're not looking. So now I want to look at the first interpretation that is in line with manifestation. Now, this interpretation is called the consciousness collapse view. It's also called the von Neumann-Wigner interpretation. Now, I will warn you that this interpretation is not very popular amongst physicists, but as far as I'm aware, it hasn't been disproven. Now, what the von Neumann-Wigner interpretation suggests is that it is consciousness that causes the wave function to collapse. Now, this is very significant because if it's true, it suggests that our consciousness influences our physical reality, which is exactly what we're saying when it comes to manifestation. We're saying that we can use our thoughts, our beliefs, our emotions to influence and shift our physical reality. Now, there are unsurprisingly many objections to this interpretation. The most obvious one being is that it seems to put in doubt the idea that there is an objective reality, and that's because if it's human consciousness that causes the wave function to collapse, then that means that everything around us is a result of humans observing it into existence. And so this begs the question of whether, when we're not looking, is there an objective reality that still exists? Now, in the book that I mentioned at the beginning of the video, he gives the example of a rock on Mars. Does that rock exist whether or not we're looking at it, or does it just exist in a state of limbo until a human observes it into existence? I think this is a very valid objection, and it's one that I actually agree with. I do personally believe that there is an objective reality that exists, whether or not humans are looking at it. But I think the thing that we have to bear in mind here is that consciousness itself is still a complete mystery. Now, it's conventionally assumed that it's produced by the brain, however, no one has ever proven that, and there are many alternative views of consciousness. One of them is idealism. Now, idealism is at the complete other end to the spectrum of materialism that suggests that the brain produces consciousness. Idealism, on the other hand, suggests that consciousness is primary, so consciousness is fundamental to reality, and anything physical is essentially secondary to consciousness. Bernardo Kastrup has a theory which is a form of idealism, and he suggests that there is a cosmic consciousness. Now, if his theory is true, or any other idealist theory, then that would mean that there could be an objective reality that exists whether or not humans are looking at it, because maybe there is something like cosmic consciousness which collapses the wave function of all of reality. So that would leave space for consciousness to be able to collapse the wave function, whilst also preserving the idea of an objective reality that exists whether or not we're looking at it. And another two objections that I want to briefly mention, which were covered in a paper by Chalmers and McQueen, I'll put the reference for that in the description. Now, the first objection they mention is imprecision. Basically, that no one knows precisely what the meaning of consciousness is. And this raises the question of what would be conscious enough to collapse the wave function. So we've been talking about humans, but could other animals and organisms also collapse the wave function? So for example, would a monkey be able to collapse the wave function, or a dog? Or would a flea be able to collapse the wave function? However, as I mentioned, consciousness is still a mystery, so I think this is less a problem with the consciousness collapse view and more a problem with the fact that we don't understand consciousness yet. And then a second objection that they mention is the idea of dualism. Now, dualism is the idea that consciousness and physical matter are two completely separate substances. So this is, of course, a philosophical objection. Many physicists do not like the idea of dualism. But the thing is, again, with consciousness being a mystery, we can't completely rule out dualism, because there are many reasons to believe that purely physical explanations will never be able to explain consciousness. They might do one day, but we can't guarantee that. Now, I just want to briefly touch on Chalmers and McQueen's paper, because they think that actually the biggest problem with consciousness collapse theories is that there is no explanation as to how consciousness might collapse the wave function. So in their paper, they actually develop a theory as to how this might work, and they do it based on integrated information theory. Essentially, in their paper, they create this theory trying to explain how consciousness might be able to collapse the wave function. Now, it is very, very complicated, but it is definitely an interesting thing to read. So that is the first interpretation of quantum physics, which very much aligns with the law of attraction. the idea that our consciousness might be able to influence physical reality. But I now want to go over a second interpretation which relates to manifestation, specifically to the idea of quantum jumping. Now this is the many worlds interpretation. Now this interpretation actually gets rid of the measurement problem altogether, because it suggests that when a quantum particle is faced with two or more options, like in the double slit experiment for example, when the particle is faced with the option of going through either of the two slits, that instead of entering a superposition of different states, that quantum system and the universe along with it actually splits into different realities, and the number of realities that it splits into is equal to the number of options available. So in the many worlds interpretation, the wave function never actually needs to collapse. All of these different potentials simply exist in different parallel realities. So the implication of the many worlds interpretation is that there is an infinite number of parallel realities or universes. So if this interpretation is correct, then it means that there might be an infinite number of copies of us that are existing in parallel realities, so who are experiencing all of these alternative outcomes. Now this of course relates to quantum jumping, because the whole idea of quantum jumping is that you jump to a parallel reality, a reality in which you are experiencing the desired reality that you're trying to manifest. Now of course this interpretation doesn't tell us how that might happen. This is all a matter of belief, specifically in how you believe that the law of attraction works and how quantum jumping works. But the funny thing is that the many worlds interpretation is actually one of the more popular interpretations of quantum physics. It's definitely more popular than the von Neumann-Wigner or consciousness collapse interpretation. So maybe this is why manifestation works. Maybe manifestation techniques allow you to actually shift into a parallel reality in which you are experiencing the desires that you're trying to manifest. So that was my attempt at trying to explain how the law of attraction correlates to science. Now, of course, these are just interpretations of quantum physics, so it's not proven. Maybe one day quantum physics will prove manifestation to be real, and maybe it won't. Ultimately, my faith in manifestation comes from my experience of it. I found my experience in life to correlate to my thoughts and my beliefs, so that is ultimately what gives me faith in manifestation, regardless of what the underlying mechanism might be that explains it. Now, if you do want a more secure scientific basis for manifestation that doesn't rely so heavily on interpretation, then I would recommend looking into the neuroscience that correlates to manifestation, because neuroscience demonstrates how our beliefs can actually shape our perception of our reality. So I actually did a video going into this in depth. If you're interested, then I'll have it linked here. So I hope this video made sense, and I hope you managed to gain some insight from it. Thank you so much for watching, and I hope to see you in the next video.